In our previous lecture, we have seen that whenever a dielectric is placed in external electrical field, it will behave like that it has some surface charge density given by the surface bound charge density as the polarization vector into the normal vector, and it may have a volume charge density because of the polarization given by minus del dot p. Now you see, if this polarization is uniform, means this p vector is some kind of constant with respect to the spatial gradient, then del dot p is going to be 0. So in a sense, when this dielectric has a uniform polarization, then there will not be any volume charge density in this dielectric. So what does it mean? It means, let us say that there is this dielectric. So let us say there is P1 polarization here, P2 polarization at this place, P3 polarization at this place. So in this sense, what will happen? Some Q1 charge will get displaced when this there is external electrical field. Some Q2 charge will get displaced here, Q3 will be here. So there might be a scenario that there can be some kind of volume charge density inside the dielectric because of this different polarization at different places of the dielectric. So uniform polarization means that there is not going to be any bound charge volume density inside the electric, only the surface charge density will exist. However, non-uniform polarization will create this volume charge density. Now let us see how this derivation which we have seen in our previous lecture affects the Maxwell equation. So we know that the divergence of electric field in a dielectric will give us the total charge density, the free charge density, and the volume charge density due to the polarization divided by epsilon naught. Now I can bring this epsilon naught here, and since I am assuming that this is constant, means uh, it is not going to vary with space, so I can take this epsilon naught inside this divergence, or the del operator should give me the rho free plus rho polarization. Now rho polarization I know is given by minus del dot p. So I will put this value. What I will get, del dot epsilon naught E plus del dot P is equal to rho free. Or if I take this gradient divergence operator outside, I will get epsilon naught E plus P is equal to rho free. Now you see that this quantity epsilon naught E plus P, if I define it as, let us say, some other variable D, so what I will get, del dot D is equal to rho free. So the divergence of this quantity, where this D is equal to epsilon naught E plus P, is going to give us a free charge density only. Means we need not bother about the polarization vector whenever we deal with this quantity. This D is known as electric flux density. Now in the integral form, what we can see, del dot D is equal to rho free. Now I will integrate it a volume dV. So what I will get, using the divergence theorem, d dot ds over the surface S, which is going to enclose this volume V, is equal to the q free. So you see, in this equation, epsilon naught is not going to come explicitly. It is already considered inside the definition of the electric flux density. So this is one of the very good equation of the case whenever we are considering dielectric, since we now need not bother about the polarization. Now, in many of the cases, what we find that this polarization is proportional to the field in the dielectric, especially when this we have seen that the charges get displaced by a small distance. So if this displacement is small or the applied field is small, we find that this polarization is proportional to the field in the dielectric. So what we usually write it as P is equal to epsilon naught into chi E. So we write this equation. So we will put this value in the definition of the electric flux density. D is equal to epsilon naught E plus P. So what we will get, epsilon naught E plus epsilon naught chi E, or I will take E common and epsilon naught common, 1 plus chi. So you see that this D is written in this fashion. Now this 1 plus chi is usually written as epsilon r. So I can write now this electric flux density as epsilon naught, epsilon r, and the electric field in the dielectric, where epsilon naught r is 1 plus chi. Now this epsilon r or 1 plus chi is known as the dielectric constant of the medium. So this is the definition. Now, for many of the materials, this dielectric constant can be quite high. Like for water, it is about 80, and a lot of textbook gives its value for various materials. For water, I have told it is around 80, and for mineral oil it is about 2.3, and for air it is about 1.0 only, and for glass it varies from 4 to 10. So there can be so many variation in this quantity. Now here we have considered that this polarization is proportional to the applied field, the field in the dielectric. Now there may be a case when this proportionality is not there. So in that case, we say that the dielectric is not linear. When this proportionality holds, we call it as linear dielectric. Now there can be a case when this epsilon r is a function of the space or xyz position. So in that case, its value will vary depending on the position in the medium. However, for a simple medium, we define a simple medium as where this dielectric constant or relative permittivity of the medium is constant. Or in more detail, a simple medium is what? Which is linear, homogeneous, and isotropic. So what is the meaning of this thing? Linear, as I have told, that this polarization should be proportional to the field. If it is not, then it is not linear. Homogeneous means when this epsilon r is not a function of position, means it is independent of the position, then this medium is homogeneous. And isotropic means that epsilon r is same in each direction. Iso means same, tropic means direction, same in each direction, then this is isotropic medium. So a medium which is having all these three properties, linear, homogeneous and isotropic, is called as the simple medium. Now in the medium which are not isotropic, what will happen? This epsilon r, or the dielectric constant, will be a function of position, and we can write it, the equation d is equal to epsilon r e, in some kind of matrix form, where I can write the x direction, the y direction and the z direction d as epsilon xx, epsilon xy, epsilon xz, epsilon yx, epsilon yy, epsilon yz, epsilon zx, epsilon zy, epsilon zz, ex, ey, ez. So you see, this is some kind of tensor quantity. Now that this d is basically depending upon so many values of epsilon. So for this is an isotropic medium, an isotropic medium. Now for many crystals, it is possible that we can choose xyz axis such that these off diagonal terms are equal to 0. We can choose our axis such that these terms go to 0. So what we will have, dx, dy, dz is equal to epsilon xx, epsilon yy, epsilon zz, 0, 0, 0, 0, 0, 0, ex, ey, ez. So we can easily write dx is equal to epsilon xx ex, dy is equal to epsilon yy ey, and dz is equal to epsilon zz ez. Now this kind of medium is of course anisotropic, but it is called biaxial medium. Now in a case when this epsilon xx is equal to epsilon yy, so in that case the medium will be uniaxial. And in the case when epsilon xx is equal to epsilon yy is equal to epsilon zz, then of course it will become isotropic medium. So these are the various definitions of various kind of media which we may encounter in the study of electromagnetics. But for undergrad course, we will find that we are going to deal with only simple media, or isotropic media with some modifications from the definition of simple media. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and please join us in our Telegram group whose link is given in the description of this video. Thank you.